We are now approaching our final solution to risk ranking methods. The methods which I'm going to introduce now is based on the Life Quality Index approach. This approach is credited to Nathani and co-workers. Nathani and co-workers considered what is the most important thing in the life of the society. And they concluded that the most important thing for the society or each of the individual of the society is long life in good health and wealth. And on the basis on these assumptions, they defined life quality index. And for the simplification, we can imagine that the life quality index is some area. And this area is defined as a product of gross domestic product per capita, let's call them G, and life expectancy E. Here we have the equation of life quality index, G times E. We have also some Q parameter, which is constant, and it defines the work-leisure balance of given society. How much given society spends at work and how much they devote, the time they devote for leisure. But in general, for our purposes, we can imagine the life quality index as a product of G and E. And without this framework, what is the investment in safety? So, investment in safety means that we take some value of G in order to increase value of E. And when the investment can be perceived as efficient, the investment can be perceived as efficient if after these changes that we decrease G in order to increase E, and after these changes the area or life quality index at least doesn't shrink. It means that this intervention in safety or safety project was efficient for the society. However, comparing to the tanks cost effectiveness of life intervention project, Nathani would like to rather base on the expenditures into safety, in increasing the safety, done by the entire society. I remember that the approach proposed by tanks was based on the governmental intervention into life-saving project. Nathani is rather concentrated on the small expenditures on the safety which all of the members of the individual do during their lifetime. The expenditures or money devoted to the safety are quite small, are very small, and they also affect the life expectancy marginally. Therefore, they call the marginal cost or marginal investment in safety. As an example, may serve buying a car with extra safety measure. For example, we pay some extra money for another airbag in the car. In this approach, the amount of the money for this investment is small, and also it affects our life expectancy at the marginal level. Let us now formalize investment in safety. As we remember, life quality index is defined as follows. Moreover, as we mentioned, we are interested in small changes, marginal changes in G and E, and the changes also in life quality index. And as we mentioned, we are interested in that after these changes, the life quality index doesn't shrink. So small changes in GDP plus the small changes in life expectancy should be at least equal 0. So they should be greater or equal 0. So let us transform this equation, inequation into equation. Here we have Q times GD over G plus DE over E equals 0, and then transform in order to obtain the value of the of money which we are going to spend on the safety intervention. And the small changes in our GDP or money which we are going to spend equals 1 over Q times G DE over E. And let's look a little bit closer on this part. So what are the changes in life expectancy? So if we extend the life expectancy, we decrease the mortality rate. Hence, we can define the changes in life expectancy as inversely proportional, so proportional to the mortality rate, dm, times some domestic constants, CFM. And then, as follows, so changes in mortality rate can be defined as the frequency or the change in frequency that at least that one of the person died from the society divided by the number of population or population size. Okay, and now back to our equation 8. So the amount of money which is efficient from the life quality index point of view, so efficient as an intervention in the safety, is somehow proportional to the gross domestic product times this domestic constant divided by Q and how much we reduce the mortality or frequency that somebody dies. And this part, G times CFM over Q, is called societal capacity to commit resources. So this is some constant and defines given society. And this value can be taken from various standards. So this is the constant which characterize, let's say, given nation or society. In other words, the money which we are going to invest in safety, or the marginal cost, can be calculated as this societal capacity to commit resources constant times the factor how much we reduce the probability of death, or how much we avert death. Now let's us implement the life quality index and the marginal intervention in the safety into cost-benefit analysis related to the safety investment. From the calculation of risk in AMCS project, we have individual risk and also we have F&N curve. And in order to evaluate the effectiveness of our intervention, we should transform our individual risk and societal risk into some scalar risk. This value, delta F over N, is the individual risk reduction. For example, if we compare the candidate design number 1, which has no safety measure, with candidate design number 2, which have door closers, how much reduction in individual risk we have after applying this intervention. And here we have some frequency number factor related to fatalities, because individual risk from AMCS denotes that this is the probability that at least one person dies, one or more person. But in our analysis, we should also include how many persons could be affected. And this is included in this factor. And the factor is calculated over this F&N curve. So we iterate over each number of the fatalities and multiply it by the probability of these consequences. So, in other words, this is the weighted weighted average of the probability that such number of people died. So we have the risk scalar, which we derive from our calculation in AMCS. And now we can define the cost-benefit analysis and the Allard criterion. This criterion is defined by the new PD standards, and the Allard criterion is defined as the ratio of costs of the intervention, cost behind the intervention, and reduction in scalar risk. And this ratio should be lower than D times E. What is D and A? Sorry, A. A is a proportional factor. This factor allows us to transform various risk reduction and cost into the same value. In other words, cost of the investment are in monetary value and risk reduction is in life, the probability of death. So how much we reduce the probability that somebody will die. So we have the other type, various type of units used. And this proportionality factor is used to transform these various units into one. In our case, this proportionality factor is societal capacity to commit resources. In other words, we defined some ratio as a cost of the intervention, so increase in the investment by the application of given safety measure, divided by risk reduction times the how much the given society is going to pay for the saving one life from the society. And this ratio is called J value, and this J value should be lower or equal D. D is in proportionality factor, and within D we define our risk attitude. whether we are risk neutral or risk aversion. If we are risk neutral, these values should be 1. We just evaluate whether the cost of the investment are lower than we obtain from this investment. But this in proportionality factor D can be also perceived as a measure whether we include all the cost averted by the implementation of the safety measure. In our case, we would like to define our D value in proportionality factor as a 1. It means that we are risk neutral and we include all the cost averted by the implementation as a result of the fire, averted because we implemented some safety measure. So this is all the cost averted by the implementation of the safety measure. So this cost, delta D, the summary cost, which we avert, consists of decrease in the cost or cost averted related to the death of people from society. Also the cost averted because of the injury, so people can be injured during the fire, and we avert this cost of treatment, or medical treatment and hospital staying and so on and so forth. And also include the cost of the loss in property or damage caused by fire. When there is some company, we can also include the cost of, let's say, business that we have to stop our business and we don't earn the money. But for the simplification, we stay at this free part of the total cost averted by the implementation of safety measure. And the cost related to the life safety we defined as follows. So decrease in the risk, how much we save life implementing the safety measure, times the societal capacity to commit resources. And delta F is taken from the AMCs, so this is our delta Ri risk scalar factor, but for the simplification, let's call this now delta FF as a fatality. So it is the reduction in fatalities calculated by AMCs and so on. And delta D is the cost averted related to the injury caused by fire. So delta E is reduction in seriously injured. This is also scalar factor. So we have the reduction in individual risk times the weighted average of number of people affected, and times the cost of injury prevented, and we take this from the statistic. And the last one, delta D, is the reduction in damage and consists of how much we reduce the loss in property and the damage prevented from the statistics. So far we have the total cost averted implementing the safety measure, but these costs are in the 1 year lifespan. In the case of the investment in building safety, we think rather that the lifespan a little bit longer. In the case with when we use the statistical decision theory, we use 45 years as a lifespan of this building. And in our case, we also should calculate the cost for this lifespan, 45 years. And in order to calculate the discounting costs, we use some specific method. And we would like to also now to calculate the discounted value for 45 years for cost averted related to the fire. And in this case we use this formula. So this is the delta D, the cost which we calculated for 1 year, and here L is the lifespan, and zeta is gamma is the discount rate, which we use as in the case of cost 3%. And the final results from our calculations. Here we have the weighted average number of person affected. So this is taken from the FM curve. Here we have risk reduction factor for fatalities. Here we have the average, weighted average for injured people, so the average number times the number times the probability of such a number for seriously injured. Here we have risk reduction for seriously injured. All these values are taken from AMCs, and those values are related to the material damage averted. In the case of door with self-closure, this is very difficult to judge how much we avert cost in property, the damage in property caused by fire. The same situation is in the chefs, we don't know, but regarding the sprinkler system, we taken the value from the statistics that it reduces the probability of damage by 83%, high damage, and the delta D for the averted cost related to the loss in property is as follows. So this is the yearly cost averted and discounted for 45 years lifespan. So this is it. In these calculations we use SCCR taken from the statistic from New Zealand, because the problem is related to New Zealand. Also the cause of injury prevented we taken from the statistics, and as you see the effectiveness of the sprinkler system is also taken from the statistic, and the expected damage in property caused by fire in New Zealand. All this cost is transformed to the purchase parity. So we transform from the dollars to this monetary value. So this is the results of our calculations, how much we avert in the case of costs, and the final decision making based on our approach is as follows. So this is the delta D cost averted. This is the cost of the implementation and maintenance for 45 years of this system. And here we have J value. And as we mentioned, J value should be at lower or equal 1. So in this case, J value lower than 1 is in the case of candidate design number 2. So this is doors with self-closure. For chefs is very close to 1. It afford much improvement to the safety. However, the cost of its implementation is also not high. So the value of J value is very close to 1, and maybe we can consider this also in the implementation. But strictly speaking, is higher than 1. For the sprinkler system, the J value is close to 2, so it is regarding the cost-benefit analysis, ALAP criterion, it is not needed to implement. Okay, thank you very much.